This is a simple calculator in Excel that computes the gas rate using the Darcy Inflow equation for gas wells. So in the workbook, there are two tabs, one with the calculator itself. So this is the interactive tool that I'll describe in a minute. But there's another tab which has the very equation that the calculator uses. So this is the inflow equation. You can find this expression in any textbook. And this is nothing more than Darcy's law. In the case of gas, when you bring the equation of state into the equation, this quadratic differential term appears. You also notice that when you use the average pressure inside the drainage radius, this 0.75 or 3/4 term that subtract this logarithmic term appears in the denominator. So the other thing you notice is this term here, dQg, pseudoskin due to turbulence. Now, this is to do with the additional pressure losses the gas experiences when passing through the pore throats. Those accelerations and decelerations add pressure losses, and it's not really a turbulent flow, strictly speaking, as understood in fluid dynamics, but it is an extra pressure loss that needs to be accounted for, and this is called either the turbulent skin or the non-Darcy skin. Okay, we can use this expression to estimate or calculate our gas rate given a certain set of reservoir and gas properties and a certain delta P, or we can use it in the other way. Given we have a certain delta P and a certain rate, we can estimate the reservoir properties that produce such a rate for that delta P. So this is precisely what is done in the first tab here. Okay, so in this tab we have a calculator that computes the gas rate using that gas inflow equation. The yellow cells are user inputs, so you can just type into them, or you can use these sliders to modify these values and see how the calculation changes in real time. So you can do this for all the parameters that you see in these yellow cells. The blue cells are calculations. Now, if you go to this cell where the gas rate is calculated, you notice the expression here, and some cells are not referenced by their typical Excel coordinates. They actually are referenced by their names. So not many people are aware of this, but in Excel you can actually name cells. So for example, this cell here, if you click over it, it's not named C8 as any other cell would be named, like E13 or E16, right? Or A6. So this cell is called KHMDFT because I named it with that name. This cell here is called temp underscore R, temperature ranking. This is called Z gas, and so on. So all these cells are the ones that go into the formula. When you do that, it's much easier to audit the formulas you have in Excel. So this is a great feature that Excel offers. Now, the other thing you see here is this graph. And in this graph, what I've done is I've plotted the gas rate as a function of permeability for a wide range of skin values. For a set of parameters, H, PR, BHP, delta B is just the difference between those two. We have a set of curves, and each curve is showing the relationship between the gas rate and permeability for a skin value. Okay, so you have a range of skins here. Blue is the highest possible productivity. That's -5 in the range I've decided. By the way, you can come here and change the ranges if you want to expand or reduce the ranges here. The way to do that, for example, the thickness here, you'll notice that the range goes from 1 meter to 100 meters. That's the range that I've decided. If you want to change that range, you can go here to the design mode, right click into that element, and that's where you change the range. So this is linked to the cell C3, that one, thickness, and it's allowed to vary between 1 and 100. So you can just change here the range, for example, 150. Okay, let's close that out of the design mode, and now it goes from 1 to 150. Okay, so you can do the same for all the other parameters where I have these sliders. So it's up to you to decide the ranges you want to have for them. Okay, so let's go back to the chart. And as I was saying, we have a range of skin values that goes from -5 at the top, that's the blue curve, -5, and at the bottom, the skin of 10 in yellow. Now, if this looks a little bit too busy for you, what you can do is go into this filter and manually select the skin values you want to have displayed on the chart. Okay, so let's say -5, let's leave 2 there, 0, 2, 4, and let's go 6. Let's do that. So less curves. Let's add that one. Just one more there, that white gap at the top. Okay, so let's leave that. What this graph shows is the rate as a function of permeability. It's an increasing curve. That's very intuitive. The higher the permeability, the higher the rate you can produce for the same delta P in a certain H, because it's KH that goes into the equation. That's why I have the H at the top here, because I'm just plotting this as a function of K. I could have decided to plot this as a function of KH, but it's less intuitive, right? So it's much easier for the user to see the perm value here, and understanding that obviously this also depends on thickness. So the higher the thickness, the higher the rate. So the whole set shifts up, okay? Now, let's understand this again. If we move vertically in this chart along a same permeability value, what we find is that the rate we can produce increases as we decrease the skin. So we go from skin of 10 to skin of 5 at the top. That means we went from this rate to this rate. So we increase the production rate as we decrease the skin for the same permeability. Very intuitive to understand. Now let's move along a horizontal line here. That means a constant rate value. What this means is the higher the permeability, the higher the skin needs to be to get the same production rate. Okay, it's also intuitive to understand. Okay, if you have more deliverability in your reservoir, you need to have lower well performance or higher skin value to produce the same rate. So let's move across these skin curves now. If we start at the bottom curve, that's the highest skin we have in the range, skin of 10, what happens when we reduce the skin? So we move vertically up, let's maintain the permeability. The lower the skin, the higher the production rate. But also, if we move horizontally, as I was saying before, the lower the skin, or the higher the productivity of the well, the less permeability in the reservoir to produce the same rate. So there are many ways that this chart can be read and used. It could be used to estimate what the rate is for a combination of reservoir properties, thickness, permeability, and skin. And it can also be used vice versa to estimate combinations of permeability and skin and reservoir properties, thickness, delta P, from a measured rate. So this graph is great because it consolidates in the one place all these relations between rate, permeability, skin, reservoir properties, and delta P, which is the driving force that creates flow. So this band, it shifts up and down depending on these parameters you have here, thickness and delta P you create. But also overlaying this chart, I have the actual live scenario, which is the one with the current values sitting on all these cells, which are selected by the user. Okay, so this live scenario, all those parameters exactly enter into this chart with that permeability, that thickness, that delta P, and those combinations produce this rate. So there you go. I hope you find this useful and let me know if you have any suggestions for improvement. Cheers.